Hi, I'm Chad Wunderlich with Viking Pump. And in a previous pump report, we talked about the fact that our pumps are self-priming. But there's a limit to how much we can self-prime. And it's not a function of the pump, it's a function of being on planet Earth. Let's talk about why this is and what this is. You're watching the pump report. This is a gear pump, a type of rotary positive displacement pump. Its tight-fitting clearances allow it to evacuate air in the suction line to prime the pump. And once primed, it's capable of pulling even higher vacuums. This ability to self-prime is key in applications like unloading drums, totes, rail cars, and barges. But as good as this pump is at pulling the liquid in, it's always going to be limited and not based on the pump. It's based on an invisible force pushing the liquid in from the outside, and that's atmospheric pressure. While you can't see it, you're surrounded by an ocean of air. Like liquids, air has weight to it, and the deeper you go into this ocean of air, the higher the pressure. At sea level, atmospheric pressure exerts a force of about 14.7 pounds per square inch, or psi, equivalent to 1 atmosphere. You can observe this pressure with a measurement tool called a barometer. This is a mercury barometer. At the bottom is a pool of mercury exposed to atmospheric pressure. A glass tube runs up from this pool with a near perfect vacuum at the sealed top. Mercury is a very heavy liquid, so 1 atmosphere of pressure is only capable of pushing the mercury up 760 millimeters, or 29.9 inches. This means that a pump pulling a perfect vacuum could never lift or pull mercury more than that. But could we make a barometer with a lighter liquid like water? So what we've made here is a water barometer. Now, unlike mercury, water is much lighter, so it requires a much taller barometer. Mercury would be about 29 inches. Water requires over 34 feet. Now, we don't have that kind of space back at Viking Pump, so we've come to the University of Northern Iowa to take advantage of their Wellness Recreation Center. Here at the top is going to be the top of the barometer, and it stretches through the hose all the way down 3 stories below. By filling our barometer completely with water and then throwing open the bottom valve, the water column drops and then settles at an equilibrium point equivalent to the atmospheric pressure. Here in Cedar Falls, Iowa, that's about 29 inches of mercury today. Since water is so much lighter than mercury, atmospheric pressure is capable of holding a water column at just around 33 feet. This means that even for less dense liquids like water or oil, there are limits to how much a pump could lift. They depend on the density of the liquid, the atmospheric pressure, and don't forget about the NPSH requirement of the pump. So we've already established there is a limit to how far or how high the pump can pull a liquid. But what about pushing? Well, believe it or not, this little pump is rated to hundreds of psi, or dozens of atmospheres. In fact, Viking Pump has models rated to over 1,000 psi. So in terms of pushing, that's like using this little pump to push oil from the basement to the top floors of some of the tallest buildings in the world. That's nearly a half-mile up. While pumps are good at pulling, they're excellent at pushing. And that's why when you see a pump installed, it's always going to be closer to the source than the destination. Pumps are for pushing liquids. Yes, they can pull, but only because of the difference in pressure they create between the inlet of the pump and atmospheric pressure outside. So there you have it. There are limits based to how much a pump can lift, and they're not based on the pump. They're based on atmospheric pressure, which is a function of just being on planet Earth. To learn more about pump priming or to view the pump reports, please visit our website at vikingpump.com.